Welcome to the Python programming tutorial series for Climate Mathematics Theory and Application. Chapter 10, Advanced Python Analysis and Plotting. In this video, we will discover and plot two-dimensional spatial domain EOFs and one-dimensional temporal PCs. Let's begin by first importing the following in line 12 to make sure that we have all of the proper packages imported. We will be using most of these packages in Chapter 10 for our analysis and plotting. Moving on to Section 10.2, which is the two-dimensional spatial domain EOFs and one-dimensional temporal PCs. First, we're going to go ahead and create two arrays ranging from 0 to 2 pi. We're also going to create a 3D array full of zeros. So our two arrays are going to be this x and y, both ranging from 0 to 2 pi with 100 digits in between. My dat is going to be a 3D array that has the shape 100 by 100 by 10. Next, we're going to go in and define a function that iterates term by term for the two variables that are given in the parameters into this specific function. So we're going to name this function zfunct, and it is going to take two arrays, x and y. The triple nested for loop that you see on the screen will accomplish inserting each value into the mydat array in each position index. We are going to go into this triple nested for loop, and we're going to set each position in the mydat array to this computation that is highlighted on the screen. In this function, we are also going to print out the final shape of the mydat. We are also going to print out the max value found in that data set. And then we are also going to return the mydat 3D array as well. We're going to go ahead and use our specified x and y on the mydat matrix, and we are going to call this result mydata. We do get the shape to be printed out and also the max value that is printed. Moving on to figure 10.1, we're going to go ahead and set a range for our contour plot. This is going to range from -0.5 to 0.5 with 100 points in between. We're going to use this getCmap function on the color map HSV, and this will create a discrete color map that has 20 discrete colors on it. We're going to go ahead and plot our data using that PLT contour F function. We're going to plot x by y, and the data that is going to be plotted on our contour map is going to be my data in the first time index, which is that third array. We're going to use the levels maxi and the CMAP that we just created above. Go ahead and add some titles, x labels and y labels to this plot. And we also want to add a color bar with a label. Wrapping that whole block with a PLT show, we do get this original field at t=1 plot to appear. We do have a discrete color bar as well as our x and y axes ranging from 0 to 6. We could go ahead and check the shape of my data by running the shape function on my data itself. We do in fact get a 100 by 100 by 10 3D array out. We're going to go ahead and set the range for our contour plot. This time it's going to be from -0.2 to 0.2 with 100 points in between. We're going to use that color map using that discrete HSV color map once again. We're going to plot using that PLT contour F function. We're going to plot x by y, and then we are going to be plotting the flipped version of my data with all rows, all columns in the 9th index, and we are going to flip it along axis 1. Our contour plot will have the levels dictated by maxi and the color map dictated by CMAP. We're going to add some titles and X labels and Y labels to our plot. We're going to go ahead and add that color bar with a scale label just to indicate that we are unitless on this plot. Wrapping that with a PLT show, we do get this original field at t=10 to show. We have a discrete color map followed by our X and Y axes that are properly labeled, ranging from 0 to 6. Moving on, we're going to go ahead and define some new variables and go ahead and compute an SVD of some data that we are given. We're going to define X and Y as the line space between 0 and 2 pi with 100 digits in between. We're going to create a matrix of zeros that has size 10,000 by 10, and we're going to call this dA. Next, we're defining a function that reshapes a data frame into an array that has size of 10,000 by 1. We're going to name this function twoodfunc, and it is going to take arrays x, y, and a. We're going to enter this for loop, and then we are going to set each index in our A array to the reshaped of my data based on the 10,000 by 1 shape. And we are going to return this newly filled A array. We're going to go ahead and set the result of using this twoodfunc on x, y, and our dA arrays, and this variable will be named dA1. Going into the SVD for the empirical orthogonal functions, we're going to set u, s, and vh equal to the result of the SVD computation that can be found in the linear algebra package within the NumPy package. We're going to operate this SVD computation on our dA1 that was just created above. We are going to set full matrices equal to false, so then we only get the raw SVD matrices out and no extra matrices. We do need to go ahead and transpose that outputted VH matrix in order to make it our traditional V matrix that we receive from SVD. To show the accuracy of SVD, we could go ahead and compute the dot product between the dot product of U and S, and finally multiplying that by our VH matrix. This XA variable will be show us the accuracy of our SVD computation. We're going to create an array of zeros that has shape 100 by 100, and then we are going to go ahead and define some functions that takes all the entries in the first column of the U matrix, transposes it, and then reshapes it. We're going to make two functions that do this. One is going to be called dig, and we are going to go into the first column of our U matrix and reshape it and return it. Our dig2 function will go into the second column of that U matrix, go ahead, negate it, and reshape it and return that reshaped matrix. We are going to make this zeros array that has size 100 by 100, and that is going to be what is used in our dig functions. We're going to go ahead and call our umap equal to the result out of dig function, and umap2 equal to our dig2 function result. We're going to define two more functions that call upon the z functions to generate spatial data. Namely, function 1 will take x and y, and we will return our zeros matrix, which is going to be our z1 function operating on xi by yj. Our function 2 will use the z2 function that we create below. Next, we're going to define two different functions that are going to be used in that function 1 and function 2. This highlighted function will be the function of z1, and now this highlighted function will be the function of z2. we're going to go ahead and make a unique color map that can be dictated from an array of colors. Then we need to reverse the colors to make sure that they have the proper ordering. And then we're using a new colmap function on our colors array, and we are just going to set this equal to CMap. When we run in line 64, we will get two unique color maps to pop up. It is going to be CMap and CMap1. Moving on to figure 10.2, we're going to go ahead and graph the EOF of the SVD computation. We need to set up some variables, namely our size, our bounds that we're going to be operating on, and we are also going to set up a bounds underscore D, which will be a different bounds that we're going to operate on for our next plot. We are going to set up our figure using this PLT subplots function. This 221 as parameter will dictate our row by column by index. We are going to have a 2 by 2 figure with 4 plots. This first plot is going to be in the first index. We're going to plot our contour f function on xy and the flipped version of our U matrix. We are going to set our title, our Y label, X labels, and Y ticks. We also want a color bar for this first plot with label size equal to large. Creating our second plot in a very similar fashion, we're going to go ahead and go into that PLT subplots. We're going to enter the third index this time. We're going to go ahead and create a level that we're going to be using for our contour levels. And now we're going to plot our data onto that. This one is going to have function 1 operating on X and Y as our contour plot in this case. We are going to use that level variable for our levels, and we are going to use CMap1 for our color map. Once again, setting that title, X labels, and Y labels. Also printing a color bar for this specific indexed plot. Now we could go into our third plot. Using that PLT subplots with 222, we are going to enter the second index of this plot, and we're going to go ahead and plot X by Y on the flipped of the U mat2 matrix. We're going to use size as our levels, which was created at the top of this block, and we are going to use CMap as our color map. Setting all of those labels and titles in the highlighted text, also making sure that we have a color bar for this plot. Lastly, setting up our fourth plot using the PLT subplot 224. Create our level variable, go ahead and plot our contour plot using XY and function 2 on X and Y. Using the levels variable that we created, and we are going to use the color map that is dictated by CMap1. Setting our title, X labels, Y labels, and the associated tick marks. We are also going to use a PLT tight layout function to make sure none of our axes are overlapping, and setting that color bar with its label size equal to large. Wrapping this whole thing in a PLT show, we do get this figure to pop up, and we have 4 plots within this figure. We have SVD mode 1 EOF 1 by SVD mode 2 EOF 2, and the accuracies on each of those modes under each of those plots. Moving on to figure 10.3, we're going to go ahead and create a time variable, and we are going to plot a lot of lines on this plot, all dictated by different formulas. For our first plot, we are going to plot T against the negative V matrix, taking all the rows but just the first column. This is going to have a color K and a label PC1 at 83% variance. For our second line, we are going to plot T against negative V of all the rows in the second column. This will have a red color and a label of PC2, 17% variance. Next, we're going to plot t against the negative sign of that t variable. This label will have the original mode 1 for coefficient negative sign t, 91% variance. The last line that will go on this plot will be dictated by t on the negative exponential of negative 0.3 times that t value. This label will be the original mode for coefficient 2 with that formula that was just stated at a 9% variance. We're going to go ahead and set our y limit, set our x label and our y label, our y ticks, and our title. We do want to go ahead and plot a legend dictated by the location parameter. This location will actually make our legend outside of our plot, which is exactly what we want, with a font size of 20. Wrapping this entire thing with a PLT show, we do get this SVD PCs versus accurate temporal coefficients plot. We can see that we do have 4 different colored lines, all dictated on the right side by our legend. And our y-axis does show the PC of coefficients, and our x-axis shows time. Moving on to create some arrays to compute dot products. We are going to redefine that t array from 1 to 11. We're going to make a sign function that is seen in the highlighted text, and we are going to return the result of the negative sign function on the I variable. We are also going to make an exponential variable that looks extremely like the line that was plotted above. Now we're going to go ahead and create variables using the above functions. We're going to name our sign function sign, and it is going to operate on the time 10. We are going to name the result of our exponential function exp, and this is going to be our exponential function operating on 10. We are going to go ahead and print the dot product that happens between these two variables. We're going to find their variances, set them equal to v1 and v2, and we are going to print the overall variance, which is going to be v1 divided by v1 plus v2. We could go ahead and find the product of the PCs, which is going to be named v underscore 1, which is going to be the transpose of the v matrix in that first column, and our v underscore 2, which is going to be the v matrix in the second column. We're going to go ahead and print out that dot product, and we do get these results to be printed to our screen. The dot product between sign and exp is approximately 0.86. Our variance is approximately 0.91, and the dot product of the PCs is approximately 2.36 e to the negative 16. We're going to go ahead and create arrays that will be used below and check the sizes of the arrays to ensure that we can accurately compute matrix multiplication. We're going to name the sdiag variable after the diag on our s variable. Vtran is going to represent the transpose of the first 2 columns of our V matrix. We are going to create 2 arrays, B and B1, by multiplying the previous matrices together. We do have to make sure that we watch their sizes. So our B matrix is going to be made from the matrix multiplication between U and sdiag first, and then we are going to matrix multiply that result by our Vtran matrix, and we are going to transpose that result, and that will represent our B variable. For B1, we're going to matrix multiply U by S diag first, and then we are going to matrix multiply that result by the transpose of our V matrix. Going into figure 10.4, we're going to need to reshape our B matrix and then plot it. We're going to name it BB, and we are going to reshape the fourth row by all columns into a 100 by 100 array. We're going to make a scale variable being the line space between negative 0.4 and 0.4 with 25 digits in between. And we are going to create a bounds variable. We're going to go ahead and create a new CMap and name it CMap using that HSV color map with 15 discrete colors on it. Setting up our figure using that PLT figure function. We're going to go ahead and create a subplot within this figure, and it is going to have one row, two columns, and we are entering the first index. In this first index, we are going to plot the contour map between X and Y with the BB contour laid on top of it, following the levels dictated by scale and using our CMap that was made up above. We're going to set our labels, set our title, X label, and Y label, and go ahead and make our X ticks as seen highlighted on the screen. We do want a color bar for this, and we are just going to print that color bar with our bounds that were dictated above with a label size of large. Next, we are going to reshape that B1 variable and also plot it. We are going to call this new B, and it is just going to be the transpose of that B1 variable. We're going to reshape it into a BV variable, and we are going to take the fourth row, all columns, and reshape it in a 100 by 100 matrix. We're going to go ahead and enter the second index of our subplots window dictated by the number 1, 2, 2. In this subplot, we are going to plot X by Y by BB with the levels dictated by scale on our color map dictated above. We're going to set the labels, set our title, X label, Y label, and X ticks. Create our color bar using those functions we have seen before, setting our bounds and our label size, wrapping that with a PLT tight layout to ensure that nothing overlaps each other. We do get this beautiful two-plot figure to appear. We have on our left side an A plot that dictates the two-mode SVD reconstructed field at t equals 5. And then plot B on the right shows the all-mode SVD reconstructed field at t equals 5. We can see the small differences in this plot. We do have a discrete color bar for both plots going on, and our axes do span from 0 to 6. This concludes part 1 of chapter 10, Advanced Python Analysis and Plotting. Join us next time for chapter 10, part 2, a NCEP and NCAR reanalysis example.